Hi all. Hello, good morning and welcome to my session. Thanks for joining me. So I see I'm here in the group and I've found that people have already entered the classroom. That's great. So let's begin with today's agenda is that we are going to continuing with the alternating circuit. And yesterday at the end we had talked about the RLC series resonating circuit and we had seen all the corresponding condition, and the first and foremost thing is that RLC series resonating circuit happens when the angular frequency of the supply is 1 upon under root LC. So that was the condition we got. It is not that resonance would happen anytime. Resonance will happen only under a certain condition, and that condition is when the frequency of the supply is equal to 1 by root LC. A very special condition is required, and then you get the condition of resonance. Now let me continue with the same factor about the resonance part, but first of all you should also understand that AC measuring device, let's talk about the AC measuring device. You know what? The regular voltmeter or the regular galvanometer that you talked about, which measures the direct current, that cannot be employed to measure alternating current. The reason is very obvious, because the regular moving coil galvanometer or the regular DC voltmeter and ammeter, they are direction sensitive. So you should remember one thing: when it comes to DC meter, these DC meters are direction sensitive. So what do we mean by direction sensitive? It's something like that the pointer is here, one direction of current, pointer goes this side, other direction of current, the pointer goes this side. So in that regard we say a DC measuring device that is direction sensitive. Now imagine what bad state will a DC meter go in when an alternating current is passed. So this is a DC meter, and first the command says go right. Then if you talk about a household supply, the frequency is 50 Hz. That means 1 by 50 second is the time period. So now just say 1 by 50 second is the time period, and this much of time is 1 upon 100 second. So what would happen? At 0.01 second it says go right. Immediately after 0.01 second it says no, don't go right, now come left. Then immediately after 0.01 second the command says no, now don't go left, come right. So that would be a severe state of confusion. So remember, a DC meter can never be used to measure alternating supply. If at any case you connect a DC meter to AC supply, you would see that the meter would violently shake, but at the same position. That means it is constantly following the command of going right, coming left, going right, coming left. So it keeps on happening. So it remains at the same position and it violently shakes. So measuring an AC value is quite a tricky affair, but then people have found out the solution, and that is, if we employ heating effect of current, then whether the current flows towards right or the current flows towards left, in both the situation heat is going to produce, because heat is direction current insensitive. Whatever be the direction of current, if the current flows, the heat is sure to be produced. So that is the reason why we employ the property, the heating effect of current, in order to measure alternating value. So therefore this AC measuring device is also called as the hot wire instruments. Why do we call it as the hot wire instrument? Because heating effect of current that particular property is employed to measure alternating value. Now, if it is a hot wire instrument, that means you should remember the reading displayed by an AC meter is always the RMS value. Always remember. An AC meter never shows the peak value, never shows the instantaneous value. It always shows the RMS value. That is the reason why we say that the household supply is 220 volt, because a technician comes, plugs in the voltmeter, and the technician finds the reading to be 220 volt. So then the technician would say, well, the reading is 220, but then we know that reading is achieved on the basis of heating effect of current. Therefore, the value, the AC value would be the RMS value. But then another interesting thing that we had done yesterday, but still for a recap, you know, these RMS values are always added graphically. We know RMS values, they are not added algebraically. When it comes to the RMS value and when it comes to the peak value, they are always added graphically. So these are the concepts which are required, and on the basis of this, let's see what question can be formed. Okay, so let's see now. The question comes here that this is a typical RLC circuit, and you're thoroughly going to enjoy this thing. And here is the supply, and that's V. Remember, only V indicates, that is of course the RMS value. That's not the peak value. So that's a value of the RMS value of the current, and it's also given that omega is 1 by under root of LC. Now the moment this condition is given, your antenna goes high, omega is 1 by root LC. So this is the condition which is the condition required for resonance. So this is R, L and C. Alright, so what are given? V is given, R, L, C is given. Now let's go step by step. The first thing I require is this. If this is the voltmeter 1, yes, now find the reading of voltmeter 1. That's the first question to begin with. Move ahead. All right, so as we do, let me even start with myself so that we can save pretty much of time. So V1 basically is the RMS value of that, so that will be IRMS multiplied by XL. Yesterday we had seen very categorically, when it comes to RMS value, the current into reactance is valid either for the RMS or for the peak. Now this comes out to be VRMS divided by Z, and XL would be omega times L. And after that you would find one more thing, that this is VRMS is V, but the value of Z will be equals to R. Why so? Because the condition of resonance has been given, and under resonating condition the total impedance is equal to resistance. And omega is 1 by root LC multiplied by L. So this comes out to be V by R under root of L by C. That will be the reading of the device, V by R under root L by C. Essentially, this is a practice for you to calculate the RMS value and keeping the condition that a voltmeter would measure always the RMS value. All right, so this is there. Kritika has come with a wonderful answer, V by R root L by C. That's great. And Ashutosh as well. So Ashutosh is in the form right from the morning. Yesterday you had posted quite nice answers, so Ashutosh I would be expecting. Harini, Ashish, yes, even Ashish as well, you post quite good answers, so do that, continue. All right, so this is what about the reading of the voltmeter, but now there is another case, and this is the condition. Try to find the reading of this voltmeter, this one. This voltmeter, this is V2, yes. Find the reading of this voltmeter. And a little bit of surprise is awaiting you when you calculate the reading of the voltmeter 2. Please do that. Kaval Singh, wonderful. The value is 0. That's great. 0, yes. Rajshri even. Ashish, Sri Krishna Sian, Rathika, and Ambika, Kritika, Prachi, Prajita. That's great. 0. Shruti, Radhika, yes. So the conclusion is you can never trust an AC voltmeter. Now, assuming that the reading is 0, if you touch the wire, this is a live wire. This is really going to sting you, remember. And why? Let's try to see the reading for those other. Look, the value of V2 will be equals to IRMS multiplied by XL minus of XC. Remember, the net impedance of XL and XC is going to be XL minus XC. And since omega equals to 1 by root LC, XL will be equals to XC, so that reading is going to be 0. So you got to be careful when you have an AC voltmeter. So this particular question has lots and lots to teach, so you people have to be careful about that. Deveshwar and Harsh, yes, that is 0. Wonderful. All right, now guys, there is another thing, and that is called as the Q factor of an alternating circuit. So let's see, how do we define Q factor of an alternating circuit? There is no as such full form for Q factor. Some people call it as quality factor as well, but this word Q is very commonly used in different arenas of physics, like even in nuclear physics, the Q value, and even in semiconductor, the Q point. So why is the Q point used? Q point को क्यों यूज किया जाता है मुझे इसके बारे में पता नहीं है. The letter Q. So Q को क्यों यूज करते हैं? Not in this speaker, sorry for that, but at least you can enjoy the language pun, what's being intended. So the Q factor, if you see here, is basically, there are lots of significance of the Q factor, but let me be very specific because there's no point we start going into that. And there are many definitions of Q factors. So out of that, the first one is this. The Q factor is the peak voltage across a inductor by peak voltage of the supply. But yes, at resonance. So at resonating condition, the ratio of peak voltage across the inductor to peak voltage of the supply is called as the Q factor of the circuit. And since it is at resonance, so we also call this as the peak voltage across capacitor to peak voltage across the supply. Because you should remember, at resonance, we all know the peak voltage across the inductor and the capacitor would be same. Reason being, XL is equal to XC. So let us see how much that Q factor will come. That Q is I naught times XL divided by I naught times Z. Just keep on watching, because peak voltage will be I peak into XL and the supply is I peak into Z. But it is at resonance, so what we can do is that XL is omega L and Z can be written as R. Not every time Z would be equals to R. But yes, specifically at resonance, that will be the case. And at resonance, omega would be 1 by root LC into L divided by R. So the Q factor would come as root L by C multiplied by 1 by R. So that's a Q factor of a given circuit, of an alternating circuit, and this is the value that you need to memorize. If you are lucky enough, a direct question you would get to calculate the value of Q factor, and that will be the direct case, or people may ask the definition wise. But shortly we'll see that the Q factor can also be alternatively defined in other ways. And there is another interesting thing I will be talking about. Okay, so the next thing that I would like to talk about is the situation which is called as the half power point. Now, what is the meaning of that half power point? Let's try to understand. In fact, this half power point finds a very great significance and a very great importance when it comes to situations like communication engineering, where signals have to be broadcasted, like the radio signal, the television signal, there are lots. So the meaning of half power point is that frequency where the average power is half the average power of resonance. So that's how we define. Now, let me not waste the quality time by deriving. Let's directly go with the case of, straightforward application. The half power point has lots of characteristic. Number one is mod of XL minus XC, that is equal to R. That's a characteristic of half power point. Whereas mod of XL minus XC was 0 when it comes to resonance, but at a point where power is half the resonance, this relationship would be valid. Now the second relationship, the phi would be equals to plus minus pi by 4, because recall tan phi is mod XL minus XC by R. So the phase difference between the current and voltage would be 45 degree, both the situation inclusive, current leading, current lagging, depending upon whether X is greater than XL or X is less than XL. The next thing, the power factor would be equals to 1 by root 2, and the power factor doesn't mind of positive or negative, because cos positive theta, cos negative theta, both are equal to 1 by root 2. And the next thing is that the value of I peak will be equals to I peak resonance divided by root 2. Those are simple calculation, we can easily do that. So that's called as the half power point, the entire characteristic. So now let's try to see how can the half power point be visualized in terms of the peak current versus frequency graph. The typical graph was this, and essentially the half power point lies there. So this is the half power point where the peak current is root 2 times the 1 by root 2 times the current of resonance. And then other important part, this is the situation of 1 by root LC, and here this is at one frequency which is omega 1, and this is of another frequency which is omega 2. So at frequency omega 1 and frequency omega 2, the power involved with the circuit is half. That means in this peak the power is greater than half, and here the power would be less than half. That's quite simple. I'll just give you a slight hint that why are people so much interested about this in communication engineering, and the reason is that while allotting frequency to different station, typical example of, let's say, frequency allotment to radio stations. You might have noted that, recall any of your favorite FM station, anything, the frequency of that will be between 88 megahertz to 108 megahertz. You think for any of your favorite FM channel, you would get the frequency between 88 megahertz to 108 megahertz. So the government authority, while allotting the frequency, they have to keep a certain minimum gap between one station and other station, and the gap maintained is this, so that while you play one station, the other one is not going to interfere. So that is what happens. Now let's try to see another thing. This particular fact, here, this particular fact is called as the bandwidth, and that bandwidth is defined as delta omega, and that is equal to R by L. Remember, that is the bandwidth of a given circuit. Recall, L by R was the time constant, so L by R has a unit of time, R by L will have a unit of frequency. And many times it's also been represented as twice of beta. And what is beta? That is very simple. Beta is equal to R by 2L, and that is also called as the damping factor of an alternating circuit. So damping factor, that means damping, the resistance value in fact decreases the signal, attenuates the signal, so that's called as the damping factor. Now we'll talk about the damping factor as well, because this is the part generally I have found that students pay less attention during their preparation. Well, if you have done so, please ignore my statement, but this is my experience generally. And there are some good questions which come. This one is already a good collection of questions, a landmine of questions you get there. And here also you get these questions. Now let's see. First of all, Q factor is also alternatively defined as, Q factor is also alternatively defined as omega resonance divided by delta omega. The same Q factor, one way we had defined as the voltage across the inductor by voltage peak at resonance. This is also the definition of Q factor. Let's see. Omega resonance is 1 by root LC, and delta omega is of course R by L. So you get this as under root of L by C multiplied by 1 by R. So that exactly matches with the previous definition of Q factor that we have talked about. So this is another important definitions of that. And finally, one ending point about the damping factor. Let's try to see what a small damping factor and a large damping factor would mean. Let's try to see that. And it is something like this. Just remember one thing. Suppose if I say, let's say L1 equals to L2, C1 equals to C2. That means, and let's say R1 is less than R2. So this is the condition. In both the situation, omega resonance of 1 will be equals to omega resonance of 2. That is clearly expected because omega resonance depends on L and depends on C. But together you get one thing, that the bandwidth, or let's say beta of 1 is less than beta of 2. The damping factor of the first is less than damping factor of second. And this implies the bandwidth of first would be less than bandwidth of second. Now don't say that bandwidth less is drawback, because we Indians are good at bargaining. So anything less means we think that that is bad, but it is not. Lesser bandwidth means the curve would be sharper. And you can think in this way, lesser damping is always a better thing. So beta 1 less than beta 2, that's always an advantage, you would get that. And next, let's see, if I say I peak at resonance for 1 would be greater than I peak for resonance at 2. Recall it, the peak current at resonance, the peak current at resonance is V peak divided by the resistance. So you should remember that resistance less, that means the peak current would be larger. So therefore I said don't go for a typical bargaining habit that, oh, the bandwidth is less, so this is a drawback. No, a lesser bandwidth is always an advantage. And I'll just show you a comparison of how the lesser damping will turn out to be an advantage for the given case. And this is something like this, say this is the given case here, this is the peak value, and this is omega. So this is for, you know, let's say beta 2, where beta 2 has a certain, beta 2 is for this, where R2 is greater, has a certain damping factor, and there is a certain value. But unless I make beta 1, you're not going to see that comparison. And this is beta 1. So this will be beta 1. Now just look, interestingly, for both beta 1 and beta 2, the resonating frequency is same, but the peak current, I think R1 less than R2, so this has to be opposite. Never mind, R1 less than R2, beta 1 less. So, oh, that's fine. That's fine. That's perfectly fine. Beta 1 is less, and therefore peak current of resonance 1 would be higher than peak current of resonance 2. So you could see one thing, that lesser is the resistance, you know, less would be the damping factor. So the width would be less, the width is less, but in turn the peak current is higher. And if the width is less, in the same frequency spectrum, the government body can allot maximum to, or the government body can allot frequency to maximum station because the width is lesser. So in that way, that's always advantageous. And on top of that, the current is high. And if the current is high, that's always a better thing in terms of the resonance part. So guys, this is how we understand about the Q factor and other parameter. So just be attentive to this thing. Now, the next part that I will be talking about, you know, we are done with the AC circuit, but there is a small combination different from this, and that is called as the LC oscillation. Now let us see what is the meaning of LC oscillation. First of all, talking about LC oscillation, it's something different from this topic. No AC involved there. You would see one thing, RL, RC combination have been done, and this is the LC combination. The first characteristic feature, all of you know that in an LC circuit, since resistance is absent, so there would be no damping. So that is the ideal world. There would be no resistance. But in practice, no matter how better conducting wire you keep, no matter how better, but still you would see that a little bit of damping would always be present. But here, let's talk about the theoretical part. So there would be no damping at all. So it is something like, you can draw an analogy with this situation, that there is a simple pendulum and no friction, no viscosity, nothing like that. So in that given case, if you oscillate it, you would find energy would simply convert between potential to kinetic, kinetic to potential, and somewhere here that would be combination of both kinetic and potential. But in any given case, loss is never going to happen. The energy simply oscillates between potential to kinetic and vice versa. In the similar way, here you would simply find that energy oscillates between electric and magnetic. Because see, The L does not dissipate, it's a pure storing one. C does not dissipate either, that's also a pure storing one. And apart from that, U magnetic, that is 1/2 Li square, and U electric, that is what, Q square by 2C or half CV square, whichever format you may wish, that's how it goes. So how does a typical LC circuit work like? It's something like this, say. This is a typical LC circuit. Some people also call it as a tank circuit. It's all the same thing. So this is how a typical LC circuit is there. Right now the circuit is open, no exchange, nothing is going to happen. Analogously, you have deflected the pendulum and you have just held it. You haven't released it. The moment you start releasing, then the drama of energy conversion would begin. And here I started with plus minus Q naught. Q naught is the maximum charge in the capacitor. As of now, you could see that the current is 0 since the circuit is open. And if I close the circuit here, now the charge would start flowing in this way. And the charge starts flowing, that means electric energy will start decreasing, but not to worry, that fall in electrostatic energy would appear in the form of magnetic energy. So this happens that the charge will reach 0, that time the current will reach maximum. And after that again current would reach 0, the charge would reach 0. So that current would reach maximum, the current charge would be 0, charge maximum, current would be 0. So that conversion keeps on happening. Like the way energy toggles between potential and kinetic, the same way energy here toggles between electrostatic and magnetic. And this process goes on and on and on. But in practice, the bad man is there. The resistor is there. So that particular resistor is going to, dissipate the energy. So slowly and steadily, in practice, finally everything will die out. Like in case of pendulum, after number of oscillation, it will again come to settle at the mean position. Exactly in the same way things would happen. Let's do question. And to begin with the question, questions are very technical and quite simple if you know the idea about that. So L and C, that's a given situation. This is C and this is plus minus Q naught. It's not necessary that you begin the circuit with the full loaded capacitor. You can also begin the circuit with full loaded inductor. That doesn't matter. Like have an analogy to the pendulum. You can start from the mean, you give a kick, or you can start from the extreme, you release it there. That point is completely an open option. So here my question is, the first question is there that you need to find the current in the circuit when charge in capacitor is Q naught by 2. Yes, please proceed with this. By the time the charge in the capacitor reaches Q naught by 2, how much will be the current in this circuit? Try out. Shivans, is there any parallel combination of these circuits? Parallel combination of which one, Shivans? If you can be a bit precise more. Shivans, LCR circuit parallel is not exactly defined in the syllabus, so I prefer not to discuss that. All right, there are lots and lots of ways to explore the circuit. So given the time span we have, I would just be very picky on that point. Okay, so I got the option Q naught by 2 under root 3 by CL. But still, Shivans, any question you find trouble, you can always discuss it in the doubt session that we have. But in the class, I prefer not to discuss. All right? Hope you understand that. So Q naught by 2 root 3 by CL. All right, so let's try to see how much will be the value. That's not going to be, 0. And this is something like this. See, when the charge in the capacitor is Q0 by 2, think about energy conservation. The initial energy is Q0 square by 2C. That's the initial energy. The magnetic energy is 0. The entire energy starts from the electrostatic one. And then the magnetic one, later on, that will be Q0 by 2 whole square by 2C plus 1/2 Li square. What did we do? We are basically equating the initial energy with the final energy. The initial energy is this much, so this will always remain there. And this 2 gets cancelled here. So this will be 3 by 4 Q0 square by C equals to Li square. So I is going to be root 3 by 4 LC multiplied by Q0. So you can, sorry for that, you can even do root 3 by 2. That is the option which is open. So that's how you find. Now let me see. So that is the given situation. Q0 by 2. Yes. Shivans, if they are connected across DC, then you need to use all those property. You may get it. I can't deny the fact that you won't get the question. But then you need to use the property, whether at beginning T0, T infinity. So those sort of question would be there. You just do it and we may talk about that. All right. So this is the value of the current at the instant when the charge is 1/2 of that. Now, apart from that, let's discuss another case. Right here, in the same question, that find di by dt at this instant. You need to find di by dt at this instant. You should remember one thing, that the current at this instant is this much. But this current isn't constant, it is varying because the energy is constantly fluctuating. So if the current is varying, we would also be interested to know that at what rate is the current varying. So please try for that. Rathika Natraj and Sri Krishna, that's great. Shivans, there is no specific theory for RLC parallel DC supply. You don't have that specific theory for that. There are only application based numerical. Okay, Navneet has come with Q0 by 2 LC. Yes, Navneet, this is correct. And Alaukik, Q0 by 2 LC. Wonderful, Alaukik. Great. And Kritika, Q0 by 2 LC. Yes, perfect. Now say, first of all, just try to realize this thing, that when you have to first verify, although we have done it, since the current or the energy transfer constantly happens between electric and magnetic, so you need to understand that the current isn't constant. And if the current isn't constant, that is varying. So how can you find? You can always do one thing, that since they are in parallel, the potential difference across inductor is potential difference across capacitor. So this was one aspect of solution, and there is another aspect of solution, and the inductor is L di by dt will be equals to Q naught by 2C, and this will give me di by dt is equal to 1 by 2 Q naught by LC. So that is the rate at which the current varies at this particular instant. I'll tell you, my experience says majority, if not all, of LC circuit can very easily be solved by these two strategies. The energy conservation and the potential difference equate. You can do that. Q naught by 2 LC, Kutesh, Rathika, Shivani, Kaval, Sri Krishna, Alaukik. That's great. Okay, so now this was about the LC circuit. Okay, after this thing now, let's try to go with the next short and sweet topic, and that is the electromagnetic wave. Let's see what are the point which is involved in this electromagnetic wave. So when it comes to electromagnetic wave, say this chapter is particularly for NEET as well as JEE Main. This is important, and specifically for JEE Main aspirant, remember one thing. By the way, you can watch a YouTube video called as JEE Flicks. In the official Aakash Institute YouTube, and that was a talk show organized on the basis of, or to analyze the JEE Main exam that had gone, the first phase. So after the first phase examination, just the analysis part of that, that's the official YouTube channel of there. And for the physics where I have represented, there I have said a very specific thing, and you just note it specifically for the JEE aspirant. Remember one thing, that there are certain topics which is not there in JEE Advanced, like magnetism, semiconductor, electromagnetic waves and other things. And interestingly, you would see lots of questions are put from these part which are not in the advanced syllabus, and that is knowingly done so as to create a distinction of JEE Main from JEE Advanced. And for those who are also appearing for NEET examination, you should remember one thing, that this topic is a straightforward fact-based thing, and there is always an allotment of one question by and large. Exceptions though don't prove the rule from this particular topic. And even during the long-term course, we don't dedicate much amount of time for this. This is more like an informative topic, and here we'll just see the main important thing that comes. Many of the properties you have already learnt about it, so let's try to see that. Now, to point it in this way, say for electromagnetic waves, there are, and specifically see all the past year questions of NEET, JEE Main, JEE Advanced, year by year, the solution of them are always uploaded in our official YouTube channel. So you can always watch, you can always take the advantage. A detailed solution of that is given there. So now let's see for the electromagnetic waves. In the electromagnetic waves, there are other things, something like this. All of us know the first part, that light is electromagnetic wave, and also it is a transverse wave. That's a common fact we know. And this particular light travels with a speed 1 by root mu naught times epsilon naught in vacuum. Now see, there is an interesting part you should remember, that when it comes to the speed of light, mu naught epsilon naught is in the case when it is in vacuum, and if it's in medium, the respective value of mu and epsilon would be there, or you multiply by the relative permeability. The second property is that the electric field is always perpendicular to magnetic field, is always perpendicular to the direction of propagation. And on top of that, even this is there, that E cross B, the direction of E cross B gives the direction of propagation. That's how it goes. So this is a very important part. Students generally fail to realize that on the basis of this property, lots of questions are formulated, and many times you tend to overthink and make it over complex, but rather the question is based on simple facts. Now let me show an example. Let us say, let electric field be along y direction, magnetic field be on negative z direction. So electric field is traveling in y, magnetic field is in negative z, so it implies the direction of wave j cross k is I, but there is a negative 1, so that will be minus of I. That's all. By the way, say, wait a minute, let me do it in this way. Erase that. Let's do this. Electric field is in z direction. We will not write positive z and negative z because the electric field continuously fluctuates. Please correct that part. Because the something like this, if there is a wave and a string is there, the particle will be confined to both the direction. It would be oscillating up as well as down, while the wave would be traveling in one direction. So the previous part that I wrote was at any instant, but that doesn't matter. Now let's come there. Electric field is in z direction, magnetic field is in y direction. We don't write positive z, negative z. After all, it fluctuates. Hope that is clear. So it implies the direction of wave, see, k cross j, that's going to be negative of x direction. That would be the direction of velocity. Now typically, see, how can, I think you got that, k cross j is minus of I. How would the wave be represented? That would be represented in this way. Ez is equal to E naught sine of omega t plus x by c. Recall the wave lesson. This is the direction of the wave, x direction. But since the wave is traveling in negative x, the sine of t and the sine of x should be same. And similarly, the magnetic field B in y direction is B naught, again sine, though that property I haven't written it, I'll just write it shortly after this, and that's t plus x by c. So normally what happens is that you would be getting that for this given condition, which of the following pair is possible, and people tend to overthink. So generally, out of 4 options which are given, you just need to think that which is satisfying the condition that is very much essential. Another interesting thing that you could notice there is the magnetic field has been written in sine, the electric field has also been written in sine. So this is another characteristic of electromagnetic wave, and that characteristic of electromagnetic wave is, see, you saw that E be perpendicular to C, and that is that electric field and magnetic field oscillate in perpendicular plane, that is very much known, but are in phase. Now this is very, very much important. They oscillate in perpendicular plane, but they are in phase. That's why you could realize that when electric field is written in sine, this should also be sine. Imagine if this was sine, this was all satisfied, but this is sine, this is cos, we would reject that. So whenever you got to choose the correct option, you need to take care of these vital things, that E perpendicular, B perpendicular to C, and the direction is given by this, and plus the phase should be same. For those who did not take this chapter seriously, you just need to realize, you just need to understand that, you know, just a simple effort of that, and it may be a very rewarding experience, because on one hand you do a heavy numerical, high voltage numerical of rotational motion, and you devote lot of time on that for your preparation, but it may not be so rewarding as compared to this. So remember, objective examination is also about how cleverly you make your strategy. That is very, very much important. So looking at the weightage part and looking at the part where you can score more, it's always a better way. So remember, these are very, very simple things, so that can be understood. That's the characteristic here about the electromagnetic wave. Another thing about electromagnetic wave, let's try to discuss, and that topic is something like this. Say, if you talk about electric energy density, that is 1/2 epsilon naught E square. Remember, this E is simply the instantaneous value. Normally in AC circuit, small letter is reserved for the instantaneous, but in electromagnetic wave, the capital E itself is for instantaneous, and when it is the peak value, E naught is written there. So this is the instantaneous energy density. So this would of course be the instantaneous one. Likewise, the instantaneous magnetic energy density is B square by 2 mu naught. Now what I'll do is that just try to understand the instantaneous electric energy density is 1/2 epsilon naught B square multiplied by C square. I've taken it for granted that all of you know that the speed of propagation apart from 1 by mu naught epsilon naught is also the ratio of E by B. And interestingly, if you wish, I may write it here, that the speed C can also be written in this way. Here, this is the ratio of instantaneous electric to instantaneous magnetic is also equal to peak electric by peak magnetic, because the sine part and sine part, that will get cancelled. Remember, in alternating circuit we are done that for capacitor and inductor, instantaneous voltage isn't the product of current and reactance, but here both the ratio of instantaneous and peak would be valid because the phase is same. You need to understand that thing. So now let's come here. 1/2 epsilon naught B square C square, and this is equal to 1 by 2 epsilon naught B square 1 by mu naught epsilon naught, and this comes out to be 1 by 2 B square by mu naught. We started with the electrostatic energy, and finally this expression is matching with the magnetic energy density. So there comes another beautiful result, that the instantaneous electrostatic energy density exactly is equal to the magnetic energy density. Remember, E and B aren't equal. The electric field and magnetic field aren't equal, but the energy density, the electrostatic one and the magnetic one, they are perfectly equal. And there is another thing, that is U net, that is twice of UE or twice of UM, whatever you wish. That's the total electrostatic or total energy density. And start with this, that is epsilon naught times E square. That can be written there. Or you write with B square by mu naught. You can do that. So this is equal to B square by mu naught. But since this is the instantaneous value, and the value continuously fluctuates with an enormous frequency, we are always interested to calculate the average value of the energy density. And this is E square. E has sine, sine square. So the average value would be 1/2. So you get the net energy density average is epsilon naught E naught square by 2. So recall here, the average of sine square would be 1/2, but this is, you write as E naught sine, so E naught gets square sine square average is half, or you can also do this as b square divided by 2 mu naught. So this is a very, very important expression, but just try to look at the minute difference you get here. If you see the minute difference here, this is the average value net, and this is the peak, where this is the instantaneous value, only the electrostatic, and here is the instantaneous. So just be careful with this particular expression. That is very, very much important. All right, so let's continue further. It's a bit fact-based, but as I've already given the sufficient disclaimer, just try to go with that. The facts are not so difficult though. Okay, now let's talk about the next thing, which is the intensity. So how do we understand by intensity of a wave? So let's try to understand about the intensity. So to understand the intensity of an electromagnetic wave, so that intensity is the average power per unit area. So intensity, watt per meter square. Now you can always say this average power is the average energy per unit time multiplied by A. That's how you can do. And average power is the average energy density into volume, and this comes out to be T into A. So A and A gets cancelled. L by T is the velocity. So come up with the expression intensity is C times average energy density. So this is another fact. As I have said, guys, if you're lucky enough, you would directly get question as a formula based, and that would be a nice thing because it's a 4 marks. Doesn't matter whether it's from rotation, electromagnetic induction, or from this. So you need to be clever enough when it comes to this strategy. Okay, after that, let's try to see there is a vector, and that is called as the pointing vector. So let's see what is that meaning of pointing vector, and that is represented by S vector. In fact, the pointing vector is this. S vector is defined as, in class 12th level, we'll start from the definition itself. E cross B divided by mu naught. This is the first definition of pointing vector. See, in fact, like you want to purchase a mobile phone from any shop, maybe e-commerce site, or you physically go to the shop wearing the mask though, that's important. Then before you buy a mobile phone, you would like to know the specification of the set. What's the RAM, ROM, and all those given thing. In the similar way, the pointing vector is a complete specification of an electromagnetic wave. You will shortly see that this is a bundle of information, and this has so many different information as related to an electromagnetic wave. And what are they? Let's see. The first thing you could see that the direction of pointing vector gives the direction of wave. Recall the lesson that E cross B direction is the direction of the wave. So that's the first information. But there is a second information, and which is very lovely enough. Let's try to see what is that. And that is something like this. Look, let's try to understand. S is EB divided by mu naught. Remember, only E always indicates that's the instantaneous values. You got to understand that. And this particular value, now you know, E by B is C, or B equals to E by C, whatever you call. So this will be B square C divided by mu naught. That's how it comes. And now let's try to see another expression, what you get. See, if I go with this particular thing, this is equal to C, all right, let me do this thing, S average, that is C into, this is B naught square by 2. Perhaps you could make that way, because B has a sine function, B naught sine omega. So if you square that and you have the average, sine square average is half. And this value is C, this is the total average energy density, B naught square by 2. Suddenly we realize that this thing is exactly matching with the expression of the intensity of a wave. So that lies the significance of a Poynting vector. That a Poynting vector, you could see the average value of Poynting vector is always equal to the intensity of a wave. So in that regard, the Poynting vector will have a unit of watt per meter square. Such a lovely significance. So if I have said that Poynting vector gives the specification of a wave, I did not make any overstatement. I did not exaggerate. Reason, the Poynting vector's direction already includes the direction of the wave. The average value of Poynting vector also includes the intensity of the wave. So you got to remember that Poynting vector has so much of information hidden within that. So that part must be clear, and you should ensure that this thing you understand it. There is another thing, see, many times people would give, this is a point source, and the point source of light, that is P, and people would ask, at a distance R, what is the amplitude of the electric field at that given distance R? This is one logical question that comes. You know that the wave is traveling in a spherical volume. So how much will be the intensity there? Intensity is P upon 4 pi R square. P is the power per unit area. And that very intensity can also be written as C into U average. So you could see that is C into U average is half epsilon naught E naught square. So yes, now this 2 gets cancelled. So E naught square is P by 2 pi R square C times epsilon naught. Rest E naught you can easily find under root of that much. So that is another direct application and direct question based. And eventually one fact, let me write it for you. I will not be deriving it, but just you keep this thing in mind, that say this is a perfectly absorbing surface and you have light here, that's I. The pressure, capital P, is equal to I by C, and if this surface is perfectly reflecting, you know, it comes there, the pressure will be equals to 2I divided by C. So you need to understand this particular fact. Okay. Now there is another part in electromagnetic waves about the Maxwell's modification, and that is also one way which gets lots of questions. So let's try to see. First of all, if you realize in case of let's see, we are going to talk about the Maxwell's modification. Mr. James Clerk Maxwell, one of a very great theoretical physicist of the earth, had come up with nice modification. But all those cricket enthusiasts, you could say that this chapter has lots of cricketer name like First you got the Poynting or Ponting, you say, whatever, and the Maxwell. So all these Australian cricketer surname, you find it here. Now let's see what is that Maxwell's modification. To understand that, I'll just give you a small idea. First of all, say, if you talk about EMF, that is d phi by dt, whenever magnetic flux changes with respect to time. Why I'm doing it? So that you would have a nice confusion-free compilation. Otherwise, if I directly write the fact, chances are that you may get confused. So d phi by dt, and you know EMF occurs under three conditions: when theta varies as a function of time, when area varies as a function of time, and when magnetic field varies as a function of time. And these two are associated with the motion, so we call that as motional EMF. If you're following the lectures properly, I had specifically said when magnetic field is a function of time, then in that case this also induces electric field. So please just be careful. It's not about inducing EMF. Inducing EMF is a bigger picture. Inducing field is here. So we make a common rule that a time varying magnetic field will always induce electric field. And the larger picture, a time varying flux will always induce EMF. That's clear. But coming specifically to this, a time varying field induces electric field. So it means something like this, guys. What you would get is, something like this, say. I'll just try to make a good compilation of that. If you have a charge, the charge will produce electric field unconditionally. Electric field is an inherent property of charge. If you have charge, there is no condition required, electric field will be produced. But if the charge is moving, then that will also produce a magnetic field. So far we know the source of electric field is this, source of magnetic field is this. But there lies another important network, and that network is something like this. A time varying field will induce electric field, and this is what we have seen. And this was given by Faraday. But together, a time varying electric field will also give a magnetic field. And this was given by the gentleman Maxwell. And this is the idea that we want to study. That means now a complex web of electromagnetic field is created. There's a big loop that under what condition electric field is produced, under what condition magnetic field is produced. Generally, if we don't compile in this way, then it creates lots of confusion that you know the fact, but when it comes the time for recalling and recapitulating the fact, it creates a confusion. So I find this as this particularly as the master plan, that what produces what produces what, this is how it goes. Okay, now we would be interested in this particular thing. That means if I simply call the source of magnetic field, if I say what is the source of magnetic field, if I say, then specifically there are two sources of magnetic field. The first source is a moving charge, and this is what we had done very specifically. And that moving charge, or you may also say current, and this is what we have seen using all those Ampere's law and all those events, that a moving charge produces magnetic field. So Biot-Savart's law and Ampere's circuital law is hidden here. But as per the recent development, time varying electric field would also be generating a magnetic field. And this time varying magnetic field is associated with a new current, we say that is the displacement current. So that is displacement current. And now we will try to understand what are the facts associated with this. So basically, coming to this point, a source of magnetic field is either a moving charge or a current. But this was the current which was a regular current which flows in circuit, and this current would be called as the conduction current. While there is also another way how we can represent the overall mechanism, that a time varying electric field will also generate the magnetic field, and a time varying electric field is always associated with displacement current. So now it becomes very easy that you say, if you make a compilation, that if you say that is source of magnetic field, if you say there are two sources, one is the conduction current and that will be called as IC, the second one is the displacement current and that will be called as ID. Now that makes the compilation fairly simpler. That's a reason why. So that's it. Even if you stick on this, that magnetic field is always produced by current, and that current may be of two types. One is the conduction, other is displacement. That's fairly better. So that's how you can understand. So this makes the rhyming easier. And within this displacement current itself is hidden the conduction current. The time varying electric field is hidden here. So whatever we wrote this here, that is exactly satisfied in this given case. And then that Ampere's circuital law was modified by Maxwell. So here now comes the modified Ampere's circuital law, and that is closed loop integral B dot dl is mu naught times IC plus ID enclosed. So essentially Maxwell has made a very nice compilation that many changes in this expression need not be made. So just tagging a term, associating a displacement current with time varying electric field, makes the modification very easy, that you can work with the same format, and except additionally you need to add the displacement current. It is something like, if you're building a new house, then everything is open to you. You can start from any way. But if you are renovating a house, then lots of care have to be taken so that you would not disturb the original arrangement. So that's how the renovation happens. So Maxwell was renovating Ampere's circuital law. So he just tried to make least amount of injury in the existing law so that the essence and the flavor of the existing Ampere's law would also be maintained, and on that an additional factor would also be included. So that is the reason why Maxwell coined the word displacement current. So on coining the displacement current, the renovation of the house was easier with least disturbance and with least migration and shifting. Remember, it's a very tough task renovating a house. Those who have undergone this must have realized that you need to do lots of compromises. So that's what Maxwell did it. A wonderful craftsman is what Maxwell considered as in theoretical physics. Now let's try to see the expression. Let's try to see the mathematics involved with the displacement current. Let's try to see it, and then we'll finally enlist the entire Maxwell's equation as well. Now first, let's say about the displacement current. So if we want to talk about the displacement current, ID, that's why we write, and that is equal to epsilon naught d phi e divided by dt. So here is already the meaning of time varying electric field. A time varying electric field is there, ID, that's epsilon naught d phi e by dt. Now based on this, let's try to see a question. Okay, so here is a capacitor plate, and this is a capacitor plate. For those who find it difficult to compute, remember electric field within the capacitor plate is Q by epsilon naught A, where A is the plate area. Now let us say that it's something like this. This is closed. That means in the charging phase, when the capacitor is getting charged up, current would be there. And once it is completely charged, the current would be zero, because now the capacitor is full stomach, so it does not want any charge, so the flow would be zero. That's how we say. So now this is something like this. Say, first of all, in this particular space, if I say during charging, you see, during charging, what would happen? See, the displacement current is a theoretical idea to include electric field, time varying electric field to be more precise. So you don't require any physical wire for displacement current to move. You should understand the craftsmanship hidden behind displacement current, because that was all to include the time varying electric field. So in this particular space, if I say due to the charge here, electric field will be there. That's how it goes. And now during charging, you see, the charge is a function of time. It implies electric field is a function of time. If the charge changes, electric field will change. It implies that the displacement current is present. That means non-zero. So we say there is a displacement current here. Now don't expect a physical wire to happen there. As I've already said, it's just a theoretical compilation. And in the same very space, after it is fully charged, you know what happens? The charge will become maximum. And if the charge gets maximum, the electric field will be maximum, but that is constant. So yes, the charge is maximum, but the electric field is also maximum, but it is constant. So therefore, displacement current will be zero. So we are talking about this space specifically to find out, to figure out whether displacement current is present or not. Now let's go for a question. And this question is something like this. Plate area A, and I'm talking about the charging process itself. This is IC. So if there is a current here, the conduction current, it's self-understood that it is the charging process. Please calculate the displacement current in this space, that is of area A by 2. How much is the displacement current through this particular area A by 2? Please calculate. Your answer should be there in terms of IC. Please do that. You do that. Meanwhile, I'll get hydrated. It's tough summer. Okay, so to start with, we need to calculate the flux here. So first let me say the flux, that will be E multiplied by A by 2. And the electric field is Q by epsilon naught A multiplied by A by 2, where Q is the charge at any instant of time. So you better write as QT. That's how it comes. And I, displacement, is epsilon naught d phi divided by dt. And then you come here as epsilon naught d by dt of, this A gets cancelled there, QT by 2 epsilon naught, and even this epsilon naught gets cancelled. So this is half dq by dt, and that is exactly half of the conduction current. This sort of relationship, we find it here. IC by 2. Okay, Kritika, that's great. And rest all people who have voted as IC, please just understand this is half of the area, so that will be IC by 2. If the area was complete, then you would get that as IC. All right, and now we will come up with the final equation, and that is the Maxwell's equation. So what are those Maxwell's equation? Let's see. Basically, Maxwell's equation are not a new equation. You know, Maxwell's equation, yes, so I began IC by 2, Hertz coil, IC by 2, wonderful. And once it is completely charged, remember, the displacement current would be 0. Eshita, Shri Krishna, great. Now let's come to this point, guys. Maxwell's equation. The first equation of the Maxwell is E dot ds is charge enclosed by epsilon naught, and that's basically the Gauss's law. So you may be thinking that it's an equation Gauss law, then why do we call as the Maxwell equation? You should remember, Maxwell was a very wonderful chef. So if you're cooking a dish, you bring things from many different places, like wheat may come from Madhya Pradesh, and the good imlis may come from South India, and good dal may come from Punjab. So they come from all different places. But then you require a nice chef to put it in a right proportion in the mixer grinder and create a wonderful dish. So that is why we call this equation as Maxwell's equation, because it was Maxwell's far-sightedness who could see the potential in all these 4 different equations. The 4 equations we'll be talking about. He blended it, he grinded it, and outcomes is a wonderful dish that light is an electromagnetic wave, and the speed of light is 1 by root mu naught epsilon naught. That is why we give a big honor to the compiler. The second one is this. E dot dl is minus of d phi electric by dt, and that is the Faraday's law, basically. So that is the Faraday's law. And oh, this is phi m, I miswrote it, phi m. If the magnetic flux is constant with respect to time, then certainly you would find that this thing would be 0. So E dot dl would be 0. You go to the world of electrostatics. So a special case of this is electrostatic, where you write E dot dl as 0, but that exists when magnetic flux is absent or it is constant. And the third is B dot ds is 0, and that is called as the Gauss's law in magnetism. Because, you know, going with an analogy, E dot ds is charge enclosed, B dot ds would be magnetic charge enclosed, but you know that magnets always exist in dipolar form. So the consequence of this is magnetic monopoles do not exist. And the final one is this, that's B dot dl is mu naught times IC plus ID enclosed. One fact, you know, for those students who may be thinking then, all the Ampere's law we talked about, then was it wrong about the discussion of Ampere's law we discussed? The answer is no. And this is because in the previous chapter, wherever we used magnetism, there was no time varying electric field. There was only a current carrying conductor, and current carrying conductor does not produce, you know, time varying electric field. Forget about time varying electric field. A current carrying conductor doesn't produce electric field either. So what we did, the Maxwell's law in all those, the Ampere's law in the previous situation was correct in that frame. Only the factor was the source of ID was missing. And this is what we call as the modified Ampere's circuital law. So this is what you get. So these 4 equations are the combined Maxwell's equation, and that's what I said. it was the far-sightedness and the clever craftsmanship of Maxwell that he could combine and he could compile all these equations to get those big results. And then was the marriage of electric field and magnetic field. Before that, electric field and magnetic field were treated as a different entity, but Maxwell could marry these two fields, and then comes the field of electromagnetism. So this is all about, and we've completed this. Well guys, we've got so many people in the group, and it's tough summer going on in New Delhi. The air condition is an artificial one, so I find people here from Himachal, people from Goa, people from many hill stations. So why don't you do one thing, send some fresh air in the telegram, that is much needed. And apart from that, the corona cases are rising exponentially, so just try to send those fresh packet of air in the telegram. So enjoy these lessons. We'll see tomorrow with the optics. Now we are going for the light part. Till then, take care everyone. Bye bye. Thank you for your presence. Thanks for joining me.